how to do it analytically, so algebraically, okay?
Awesome.
It's not very difficult. It's pretty easy, as long as you follow a few steps, okay? So, if you have a limit allows us to explore the behavior of a function around a particular x value. We've been talking about that since day one, right? If the direct substitution yields a number, then the number is the limit. You remember when we were talking about that, guys?
Mm-hmm.
So the number is the limit. And the function does not have a hole that at the x value. Now, if the direct substitution yields a number divided by 0, the limit does not exist. If the direct substitution yields the indeterminate form is when we have a 0 divided by 0, meaning the limit can't be determined just yet, okay? More work needs to be done. And what I mean by that more work that needs to be done is there's 3 types of things that we can fall into at that point. So this is what I'm talking about, the 3 little steps that we might need to follow, okay? The best ideal limit is direct substitution. We get a value, we're done, save the day, right? But then there's times where we get that 0 divided by 0. So then there's 3 different options that we may fall into. One of them is that maybe we factor and cancel the common factors. Remember, we did that on Monday. We had one that had ended up being 0 divided by 0, and then we factored the numerator, and then we canceled the common factors from the numerator and denominator. Then we were able to go back into direct substitution and find the limit, right? So then, if the factor does not have factors or nothing to cancel, then there's 2 more techniques that we can use to find the limit. One of them is called rationalize. We can rationalize the function. And use common denominators to simplify. So, either we're going to factor and cancel, or we're going to rationalize this function, okay? Now, there is a few steps here. Look. Direct substitution. If I use direct substitution and I get a number, the number is the limit. The most ideal one, right? You follow?
Yeah.
That's the perfect one, perfect world. We love those. We get our answer. We don't have to do any more work. If we get 0 divided by 0, then more work needs to be done. And either we're going to factor and cancel, rationalize, or find a common denominator. If a number ends up dividing by 0, again, kind of an ideal type of limit where limit does not exist and we're done. Okay, so we're going to go over a couple of those examples and we'll be done for the day, guys. Sound good?
Yeah.
Okay, so let's talk about factor and cancel techniques first. When we have a rational function with a polynomials, and the numerator and the denominator have zeros at x equals a, factor both the numerator and the denominator and cancel terms. So the first thing, guys, I want y'all to get used to this first, okay? I understand, like in this lesson, we're using factor and cancel, right? But I don't want you to jump right into that. I want you to get used to running the limit first with a direct substitution method. What that means is we take the limit as x is approaching -2, and we're substituting -2 for all the x values. So we get -2 squared minus 4 divided by -2 plus 2. That gets 0 divided by 0. That's your indeterminate form. That's when we use factor and cancel, common denominators, or rationalization. Okay? So now let's try to factor. Well, the numerator has a difference of squares, correct? So we have x minus 2 and x plus 2 divided by x plus 2. So you see how a factor actually simplifies and cancels itself out? Agreed? So then we're running the limit as x approaches -2 of only x minus 2 now. And technically, every time we write a piece of this function, I know it's long and I know it's tedious, but each piece should have the limit as x approaches -2 until we actually take the limit. Y'all follow? Yeah. Okay, so now once we simplify to this piece here, we direct substitute just like what we did on the top here, but now with the simplified version. So we use direct substitution, so -2 minus 2, and what is the limit, guys? -4. So there's actually a hole, right? Where?
-4? Or no?
At x equals?
2.
-2, right? That's the factor that got canceled, the x plus 2. So the hole was actually at -2. So now we know there was a hole at -2, -4. Hence the reason why we got an indeterminate form. Because the limit was actually approaching a hole. And remember, the limit can exist at a hole, right? Okay. Let's do it again. The limit as x approaches 5 of x squared minus 3x minus 10, x squared minus 10x plus 25 being divided. Now, if we were to use direct substitution here, we would get an indeterminate form. You're going to get 0 divided by 0. Okay? So we're going to jump right into the factoring now. So the limit as x approaches 5, the factors in the numerator are
X minus 5 and x plus 2.
x minus 5 and x plus 2. Perfect. And the denominator?
X minus 5, x minus 5.
X minus 5 and x minus 5. Now we simplify. So x minus 5's cancel. So we're left with the limit as x approaches 5 of x plus 2 divided by x minus 5. Now, at this point, nothing else simplifies. So now what we do? Direct substitution. So we like to abbreviate that with d dot s, which is direct substitution. So we put 5 plus 2 divided by 5 minus 5.
7/0.
7/0. Which is?
Indeterminate.
Undefined.
It's undefined technically. So what does it mean for a limit?
It doesn't.
It does not exist.
Wait, what's the difference between indeterminate and?
Indeterminate means that something needs to be done more to the limit in order to find the limit. So when we get a number divided by 0, it's actually an undefined value, right? But remember, limits are not undefined and defined. Limits exist or do not exist. So the equivalency to that is the limit does not exist. So we put D N E, does not exist. And we're done. So what that means is that we had an unbounded behavior. What do I mean by that?
It means the graph looks like.
It doesn't like necessarily reach a certain y value.
Right. It doesn't necessarily reach an actual y value.
Yeah, it goes like that.
It goes probably to infinity,
Yeah.
right? Or negative infinity. Okay. Here. So now that we're kind of getting the concept here, what do we do first? So rationalization is actually finding what we call the conjugate. So when direct substitution yields 0 divided by 0, which is an indeterminate form, we may rationalize the numerator by multiplying the expression by what we call the conjugate. The conjugate. Meaning, if I had x minus y, the conjugate would be x plus y. That's the conjugate. So look here. If I would have went into direct substitution for a second, I would have got the square root of 0 plus 1 minus 1 divided by 1. Or 0, sorry. The limit is approaching 0. So we get 0/0. So it's indeterminate, correct? Okay. So now we're going to take this limit as x approaches 0 of the square root of x plus 1 minus 1 over x. I need to rationalize. Rationalization is technically a difference of squares. Also, you're trying to rationalize in the sense of the square roots. So do you see how this has an expression of the square root of x plus 1 minus 1? The minus 1 here is technically the indication of your conjugate. So what we're going to do here is we're going to take the conjugate of the numerator, which is the square root of x plus 1 plus 1. Now, if I only multiply the numerator, then I'm changing the whole function. So with rationalization, I have to do the numerator the same thing to the denominator. Y'all follow? So the square root of x plus 1 plus 1. Now, what we're going to do is we're going to rationalize by foiling. So if you notice here, the numerator is technically difference of squares. If I multiply the numerator out. A square root of x plus 1 times the square root of x plus 1 cancels the square roots, and we get x plus 1. Y'all see how we got that? Now, we're going to distribute the square root of x plus 1 times 1, which is going to be a positive square root of x plus 1. And then we're going to take the negative 1 times the square root of x plus 1, so we get a minus square root of x plus 1. And then negative 1 times 1 is negative 1. So do you see how the conjugate cancels out the middle term? Notice here that the square root of x plus 1 and the minus square root of x plus 1 will cancel each other out. Now the denominator, we usually leave alone. Leave it as this x times the square root of x plus 1 for a moment. Plus 1. Why we do that is sometimes we don't need to mess with it because it's easier to just leave as is. What else cancels in the numerator?
The ones.
The ones. So what am I left with? I have this limit as x approaches 0 still, right? And we're going to take that limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. Do you notice something else? I have x in the numerator, and in the denominator, I have x times the square root of x plus 1 plus 1.
Wouldn't that make it like a,
Doesn't this reduce?
yeah.
What does it reduce to? I have the limit as x approaches 0 of 1, because x divided by x is 1, right?
Doesn't it make it 0 over?
No, x divided by x is 1. 5 divided by 5 is 1, right?
Yeah.
So now I'm left with 1 divided by the square root of x plus 1 plus 1. So you see how if I would have foiled it in, or distributed that x inside, I would have had to pull it back out to simplify even more. So what we do is we leave it alone in the denominator to see if anything is going to cancel or simplify more. Now we use direct substitution since nothing else simplifies. So we get 1 divided by the square root of 0 plus 1 plus 1. So what is the limit? What's the square root of 1? 1 plus 1.
2.
So what is it?
1/2.
1/2. Are we okay there?
Yeah.
Okay. If you look here, guys, this is the graph that we just solved numerically. If you look at it graphically, what is the limit approaching for 0 on both sides? 1/2. And that's what we found. Cool? Okay, common denominator. Guys, and this is the last problem. Use the common denominator technique to simplify the function when we have fractions in the numerator. Yes?
I think it's 2:30 something. Can I watch these online real please?
Yeah. So we use common denominator if we have fractions. So do you notice here, we're trying to find the limit as x approaches 0 for 1 over x plus 4 minus 1/4 divided by x.
Isn't there like a way to like multiply the numerator by the denominator or something like that?
Correct. So what we do is we find a common denominator. The easiest way to do that is multiplying both of them by each other. So right here, is x plus 4, right? So I'm going to write an x plus 4 out here. Then I have this 4. So I'm also going to multiply by 4. And remember what I talked about earlier. Whatever I do in the numerator, I must do to the denominator, right? So I'm going to take that whole thing and also multiply it by the denominator. Do you follow? That way we never changed the actual equation. Now, if you look at the very first piece, this piece here, it's 1 over x plus 4. If I take 1 over x plus 4 times x plus 4 times 4, what do I end up with? So let's write that out. If I had 1 times x plus 4 times 4 over x plus 4, what am I left with?
4 over
Just 4,
4, yeah.
right? Okay, so now you notice that we end up with 4. So we're just going to write 4. Minus, right? Minus, what do we end up with the second fraction? 1/4 times x plus 4 times 4.
1? I don't know.
Don't these cancel?
Just x plus 4.
Just x plus 4. In parentheses, right? Because that whole thing is being subtracted. And in the denominator, I have x times 4 times x plus 4. So I'm going to rewrite that a little bit. 4x times x plus 4. I didn't really distribute anything. Does that make sense, guys? Yes? Cool. So now this is the limit as x approaches 0 of this simplified version. Well, if I distribute this negative across, I get 4 minus x minus 4. Right? 4 minus x minus 4.
The 4's cancel each other.
The 4's cancel. So I have the limit as x approaches 0 of negative x in the numerator over 4x times x plus 4. So I have negative x divided by 4 times x plus 4. Does anything else reduce? We have multiplications and divisions. What else can cancel or simplify?
The x's?
The x's. So what am I left with in the numerator? The limit as x approaches 0 of negative 1, right? Because it was a negative x, correct? Over 4 times x plus 4. Does anything else reduce?
Can you distribute the 4 and the...
You can, but there's no need.
Okay.
Because what we're trying to do is we're trying to break everything apart to see what simplifies and cancels, right? So we wanted to leave it as broken pieces so we can see what actually goes together. Does anything else go away or cancel or simplify? No. So what do we do now? Our special little method? Direct substitution. So we get negative 1 divided by 4 times 0 plus 4. What do we end up with? Negative 1/16.
Yeah.
Agreed? And that's it.
Mm.